If more rockets are moving to liquid oxygen and methane, the safety question gets bigger too. These vehicles can carry millions of pounds of propellant. A serious failure near a launch site is not just an engineering problem. It affects public safety, site design, and how close people and equipment can safely be. That is why this NASA project matters now. Engineers at NASA's Tennis are leading a final series of tests at Eglin Air Force Base to measure explosive yield in a controlled way. The work supports a three-agency effort with NASA, the Federal Aviation Administration, and the U.S. Space Force. The goal is simple to say, but hard to do. They want real data on what happens when oxygen and methane systems fail catastrophically. So future rules and launch planning are based on measurements, not rough assumptions. The test articles are not full rockets. They are controlled models of a generic fuel storage system. NASA's Wallops Flight Facility built them with liquid oxygen and methane separated by a common bulkhead, which is a shared wall between tanks. The tests cover three scales: 100 pounds, 2,000 pounds, and 0 pounds of propellant. In many runs, that separation is intentionally broken to simulate a worst-case failure. Instruments on the article and across the test field measure the pressure wave at set distances. High-speed cameras track the heat of the event, plus the speed and direction of fragments. NASA's own plane description is almost blunt: put fuel in a rocket, blow it up in a remote place, and measure the boom. But the point is not spectacle. It is to build a usable evidence base for methane propulsion safety. One revealing part of the story is how much had to be built just to run the tests. The NASA team started with a greenfield area and a remote concrete pad at Eglin. In about 4 months, they turned it into an operating cryogenic test site. Crews cleared the area, leveled the pad, and brought in storage vessels from Kennedy Space Center for super cold propellants. They fabricated about 700 feet of cryogenic transfer lines and built support stands to carry them to the test article. They added generators, converted a shipping container into a workshop, and turned the mobile control center from Wallops into the main control room. That room sits 1.6 miles from the blast site for smaller tests and will move to 4 miles away for larger ones. The scale of the setup shows this is careful field engineering, not an improvised experiment. The explosions are only part of the challenge. First, NAS to move cryogenic propellant safely in a remote place without its usual large industrial control systems. That forced the team to design a compact control approach. NASA's data acquisition system team supplied hardware that is efficient enough to run on lithium batteries and solar panels. They also adapted existing Redline software into a custom control system. Operators can watch an on-screen diagram of valves and instruments while the system handles propellant transfer and records data. Eglin crews added fiber optic lines and 3 pressure sensor arrays spaced 120 degrees apart, giving Marshall Space Flight Center's blast team the setup needed to capture detailed measurements. Before the main series began, NASA also ran baseline C for testing a cold shock test with liquid nitrogen. That sequence matters because it establishes reference data and checks the infrastructure before the more complex mixed propellant runs. NASA says the results should help shape launch site planning and safety protocols for methane-based propulsion systems. That sounds narrow, but it reaches far. If agencies and companies know more precisely how blast pressure, heat, and debris scale with tanks, eyes, and failure mode. They can make better decisions about pad spacing, stand-off distances, emergency procedures, and acceptable risk. The tests also compared different failure configurations, including transfer to failure and common bulkhead failure, which helps move the discussion from generic danger to specific scenarios. That is the real value here. Not a dramatic explosion, but a clearer safety map for a new generation of rockets. For viewers in China and elsewhere, the broader lesson is familiar. When an industry scales fast, institutions need measurement to keep pace. The SAN ASA campaign is one example of how that measurement is built.